The electric motor. The electric motor is a device that uses the force applied by a magnetic field on a current carrying wire to induce rotation. Here we shall analyze the operating principle of a simple direct current or DC motor. When we say direct current, it means that the direction of the current in the conductor is in any one direction at any given time. It is an excellent way to apply the lessons we have learned previously. Consider a rectangular coil made from insulated wire. This coil is kept inside a magnetic field as shown in the adjoining figure. A current is sent through the rectangular section ABCD. As you can see, the coil has been mounted in such a way that the arms AB and CD are perpendicularly oriented to the magnetic field. In other words, the north-south field lines are cutting through these two arms at 90 degrees. The coil is mounted on a rotating shaft and two devices called commutators are used to supply current to the coil. They also allow for the circuit to cut in and cut out briefly during each complete rotation. We will see this later. When current is sent into this coil, the coil arms experience forces in accordance with Fleming's left-hand rule. The arm AB will experience a downward force, while the arm CD will experience an upward force. Now, ordinarily, this would mean that the forces being equal and opposite will cause no movement. But in this case, since these forces are not being applied along the same line, they will cause a kind of turning effect or torque. The result of this turning effect is that the entire coil assembly will begin to rotate. As the coil goes through a half rotation, the coil ends will break contact with the commutator. When they regain contact, the current in the arms is now circulating in the opposite direction, since the positions of the coil contacts have reversed themselves. Thus, the arm AB will now experience an upward force and CD will experience a downward force. But since these two arms are now on opposite sides, the rotation of the coil will continue in the same direction. This reversal of current is repeated every half rotation or half cycle, and this is what allows the coil to rotate continuously. In real applications, the coil is made from several hundred or thousands of turns of wire, and this structure is called the armature. The magnetic field concentration in this region is increased by using a laminated soft iron core inside the coil. In large motors, powerful electromagnets are used instead of the weaker, more fragile permanent magnets. The phenomenon of electromagnetic induction. We have already learned that a current carrying conductor placed in a magnetic field experiences a force. But what happens if we move a conducting material inside a magnetic field? Michael Faraday investigated this possibility and came up with some important results. These results taken together constitute a study of the phenomenon called electromagnetic induction. Let's look at two experiments to understand what is happening. The first is the coil magnet experiment. Take a cylinder of cardboard or paper and wrap several hundred turns of conducting wire around it. Connect this wire to the two ends of an ammeter or a galvanometer. Now, take a bar magnet and insert it into one end of this coil and then remove it from this coil. You will notice that when you enter the magnet into the coil or when you extract the magnet from the coil, the galvanometer shows a deflection. You will also notice that if the magnet becomes stationary, no matter whether it is inside or outside the coil, the galvanometer shows no deflection. Even more interestingly, the directions in which the galvanometer deflects are the reverse of each other when the direction of the magnet reverses. For example, the direction in which the galvanometer deflects when you enter the coil is the opposite of the direction in which the needle will deflect when you exit the coil. The twin coil experiment. In the twin coil experiment, we have taken a soft iron core and we have wrapped two separate coils around it. The first coil can be connected to a power source using a key, and the free ends of the second coil are connected separately to a galvanometer. Please note, both of these coils are insulated from each other. there is no direct electrical contact between them. There is no flow of current between them. Now, open and close the key of the first coil and observe the behavior of the galvanometer. You will observe that whenever you make or break the circuit, in other words, whenever you insert or remove the key, there is a small momentary deflection in the second coil. The deflection's direction will reverse itself depending on whether you are closing or opening the key. So what do these experiments tell us? There is some kind of rule that governs the direction of the induced voltage and current. And there is a very simple and effective memory aid that helps us to predict the direction of the induced EMF if we know the direction of the magnetic field and the direction of the conductor's motion. Hold your right hand parallel to the ground. Stretch the thumb out and the index finger and the middle finger and orient them in such a way that they are all perpendicular to each other. They should all be at 90 degrees to each other. If the thumb is pointing in the direction of motion of the conductor and the index finger is pointing in the direction of the magnetic field, the middle finger will automatically point to the direction of the induced current. This is Fleming's right hand rule. It is also called the generator rule. The electrical generator. Adjoining is the figure of an electrical generator. This is a simple schematic diagram. One of the things that should strike you immediately is how similar this diagram is to that of the electrical motor that we covered in the previous section. And this is not an accident. The two devices are working on similar principles, they are just working in opposite directions. While in the earlier case, we were converting electrical energy into mechanical energy, here we will convert mechanical energy into electrical energy. As before, we have a rectangular coil ABCD. This coil is placed between the poles of a magnet in such a way as before, the magnetic field passing from the north pole to the south pole cuts through the arms AB and CD perpendicularly. The ends of the coils are attached to two split rings, and from there the entire arrangement is mounted on a rotating shaft which allows us to rotate the entire coil. Let us say we rotate the coil in such a way that arm AB moves up while arm CD moves down. According to the generator rule that we just understood, this will induce a current that will be moving along the path ABCD or clockwise if you view it from the upper side. As the coil goes through a half rotation, we notice that arm CD, which was earlier moving down, will now start coming up, while arm AB, which was previously moving up, will now start going down. As this happens, the relationship between the direction of motion and the magnetic field is changing, and as a result, the direction of current will reverse itself. If we allow this state of affairs, what we get is an alternating current, which means that the direction of current will switch back and forth constantly. And a generator that uses this effect is called an AC or alternating current generator. If we want a DC output, we have to again use a device called a commutator, which allows the circuit to break and be made again in such a way that the direction of current will always remain constant, either clockwise or anti-clockwise. In India, the majority of generation of electrical energy using this device is in the AC form or alternating current form. The current switches direction 100 times every second, so the frequency of this alternating current is 50 Hz. DC finds niche applications on smaller scales because it requires a rather delicate and expensive commutation assembly.